Okay, let's get going. So, continuation of our exploration of molecular geometry optimizations. Today we'll look at the transition states, at what they are, at how to find them and how to diagnose them and what to do with them to an extent. So let's say we've run our calculation and the program has arrived at a point where the gradient is 0. And it has triumphantly reported to us, converged. The gradient is 0, this is a stationary point. But of course, which stationary point? The gradient can be 0 in a maximum as well. In a saddle point, that could be maximum with respect to some coordinates and minimum with respect to others. And to illustrate this kind of diagnostics, let us consider just a one-dimensional case, a quadratic potential. Right, just a ball on a spring, so kx squared over 2. And as you know, if k is positive, then this has a minimum. If k is negative, then this has a maximum. And so the diagnostics really here, the curvature, the quadratic curvature at that point is the second derivative. It's the coefficient k, the force constant. And if k is greater than 0, then we have a minimum. And if k is less than 0, then a maximum. Now, this is a mathematical formulation of that. A more physical thing is if we consider instead the vibrational frequency of that ball on a spring. So we say, okay, F equals ma, the force is the gradient of the energy minus, so things move downhill on the energy surface, that's where the forces are pointing. So ma is the derivative of that, and those of you who did classical mechanics or vibrational spectroscopy would remember that after a little bit of math, you arrive at the expression for the vibrational frequency. And then if k is positive, then this root is real, and then we have a minimum, and if k is negative, then the root will be imaginary, and then we have a maximum. So it's a different way of defining things. We run vibrational analysis, and if all the frequencies are real, then we have a minimum, and if some are imaginary, then it's probably a saddle point, and in the unlikely case when they're all imaginary, then we got ourselves into an energy maximum. And this is one-dimensional case. If we work through the multi-dimensional case, when we have multiple interacting particles moving, we calculate all mixed and straight second derivatives with respect to all of the coordinates. That is going to be a matrix because there are second derivatives with respect to all of the coordinates there are. You may remember from your vibrational spectroscopy, then the diagonalization gets you normal mode vibration frequencies and the directions in which the atoms move when a particular vibrational mode is activated. What is important is when you look at these Hessian matrices in multi-atomic systems, you will see 6 eigenvalues which are 0 or close to 0, well, as much as machine precision permits. And this is to do with the overall translation. Of course, in vacuum, if we move the entire molecule uniformly in any of the 3 spatial directions, the energy is not going to change. And so k is 0, and therefore we have a 0 eigenvalue in the Hessian for that degree of freedom. And the 3 other ones are the 3 rotations. So the molecule can be rotated overall in 3-dimensional space, and the energy doesn't change. So any Hessian that you have will have 6 near 0 eigenvalues, and a lot of software packages are essentially diagnosing this automatically, and they're not even printing those 6 0 eigenvalues to you because they know that they will always be present. And so that is a diagnostics table from this book here, thoroughly recommended. Comes with Gaussian when you buy the very expensive site license. It's on the bookshelf in the office. If you have a minimum, you need 0 imaginary frequencies, right, corresponding to all the k's being positive. If you have 1 or more imaginary frequencies, then that's a saddle point, not a minimum. You need to revisit your geometry, push it out of that saddle point and reoptimize. If you are fishing for a transition state and you don't have any imaginary frequencies, then it's not a transition state, it's a minimum. A true transition state must have exactly 1 negative eigenvalue corresponding to a maximum along some reaction coordinate, meaning exactly one imaginary frequency. And if you've got more than one imaginary frequency, then that's a higher order saddle point. It's a maximum with respect to multiple coordinates, and this is probably not something that you want. So when you're looking for minima, you are looking for strictly positive semi-definite Hessian, and if you're looking for a transition point of some kind, you need exactly one eigenvalue of the Hessian to be negative, and therefore exactly one frequency imaginary. As you can imagine, this involves the calculation of the matrix of second derivatives. In a typical molecule, you would have a couple of hundred atoms, so north of 100, possibly in the thousands coordinates. And so this matrix of second derivatives could be large. As you will see in the subsequent lectures, response properties like atom displacements are quite expensive, and so Hessians are pretty hard to compute, as you will see in your practicals. And so ideally we should compute them as little as possible. Typically this is done at the final point of the optimization, and this diagnostics is done, and you are satisfied that your molecule is something or something else that you require it to be. So practical considerations for optimizations as well, various pitfalls in which one can fall. Of course, molecular symmetry. If you started in a symmetric molecule, energy is invariant with respect to that symmetry, and therefore its gradient. So the gradient conserves molecular symmetry. Any step down the gradient will likewise conserve that symmetry. And it is your responsibility to check for symmetry breaking in various d-element complexes, for example, with degenerate ground states. Degeneracy can be lifted through Jahn-Teller effects, so chemists know what that is, but that creates non-symmetric minima in molecules that are themselves chemically, by the structure and the bonding, actually symmetric. So checking for these things is your responsibility. Then again, Cartesian versus internal coordinates, correct choice will significantly accelerate your convergence. In particularly badly chosen coordinate systems, the geometry might not even converge because the displacement would never be small enough, or the gradient would never become small enough because the point cannot be reached in which it is. And then if we are dealing with a multi-level optimization, so let's say you have a large protein, and it is generally a good idea to first optimize it at the very low, cheap level, like semi-empirics, to get the geometry roughly correct. And of course, at the end of that calculation, you can calculate the cheap Hessian and use it as the initial guess for the Hessian of the expensive method that then BFGS can start with and update it at every iteration. And that can conserve a significant number of iterations using the expensive method, and sometimes actually literally weeks of calculation time. That's an example, geometry optimization performance in various types of coordinates. So internal are just the Z matrix, Cartesian is pure Cartesians, and mixed is a judicious choice of whoever set up the calculation as to which should be which. Different molecules in here, histamines, the one of the largest and the messiest ones, histamine hydrochloride, I think, in this case, or positive cation. And if you look at the number of variables firstly here, right, histamine has the most, and in internal coordinates, the optimization converges in fewer steps than the raw coordinates. This is truly a testament to how sophisticated the optimizers are these days in quantum chemistry, but in Cartesians, it's not converged even after 100 iterations, and then mixed is somewhere in between, right? So in these cases, for example, for anthraquinone here, the choice is basically inconsequential, but for this bicyclopentane, it's a factor of 2 that you can save in the calculation if you choose appropriate internals. And for CH and O chemical molecules, this would normally be just the Z matrix. Okay. Now, let us talk about transition states. So the previous slides were about how to identify the type of stationary points that you have. Now, let's say you are fishing specifically for some reaction intermediate. How do we find one? Well, okay, this is the Hessian, and imagine we've diagonalized it. So we went into as a coordinate system that diagonalizes our second derivative matrix. And if we have a minimum, then that number would be positive, and so delta x will step in the negative direction of the gradient, and so that minimum will be refined. However, if that number is negative, so we are close to a maximum with respect to that particular coordinate, if that's negative, it would cancel with this minus, and so the step will be made in the positive direction of the gradient, meaning further uphill. So if you are close to a minimum, Newton-Raphson optimizers will drive you to a minimum. But if you are close to a maximum, they will treacherously drive you upwards into that maximum, right? It locates the nearest stationary point to where you had begun. And if you're looking for a minimum with an awful initial guess, that is probably a problem. However, if you are looking for a transition state with an excellent initial guess, then that's great, because it's actually going to get you into that transition state without too much trouble. There are numerical troubles there. I will not bore you with the details of all of this. Remember quasi-Newton from the previous lecture. We were updating Hessian approximately using the history of the gradients, using the BFGS. BFGS can become unstable if the Hessian is not positive definite. In that case, there is a different, slightly more complicated update scheme called Bofill update, which also allows one to do quasi-Newton optimizations, but this time of transition states. And that's a famous picture from this lovely paper. That's your reactants, that's your products over there, that's a minimum and that's a minimum, and that's a complicated looking transition state. And if you start somewhere nearby, then the straight Newton-Raphson or quasi-Newton with Bofill update will get you into this transition state, and you will have your reaction intermediate optimized, and that gets you the energies and the entropies and the enthalpies, and therefore certain approximation at the reaction rates if you do everything correctly. Now, how do we do that more systematically? Imagine we don't actually know what the transition state is, that we are fishing for, well, a research-grade question as to what is the intermediate in a particular chemical reaction. We would know the geometry of the reactant, we would know the geometry of the product, and then we can define the intrinsic reaction coordinate, and that is the minimum energy path on one of those surfaces that connects reactants to products. So the path that at every point is a minimum with respect to every coordinate except the direction of the path. Right? That's called the minimum energy path. And variationally speaking, right, that's the integral over the energy over some path, and the variation with respect to that path would have to be zero, and so that is our stationary energy path. That's an example from the work we have published some years ago. You are looking from the top at a complex of a lanthanide ion. So this is dysprosium here, and that's the daughter cage, so cyclic amino tetramine here with some side chains. And in liquid, it can isomerize, so this CH2CH2 can twist around, and so this red atom goes in there and the green atom goes in here, so this corner got itself twisted out. Of course, this can happen to all of those corners, and eventually all the reds are on the outside and all the greens are inside, and you can imagine the path is quite complicated here. You can invert them simultaneously, you can invert them one at a time, and we've mapped out that path after quite a lot of calculations. In this case, there are minima that are very high in energy and therefore unlikely. There are minima that are more likely, and so you've got this one at a time isomerization process. But these are all energy minima, and in between them there will be those intermediates corresponding to a local maximum on the reaction path. And if you read that paper, you will see all of those energies calculated using a variation of this intrinsic reaction coordinate method. So how would we go about finding one? Well, we can start in a particular geometry and take a step right, a particular coordinate, for example, pull some bond and fix it. Then at that point, we can re-optimize every other coordinate into a minimum. Now, by definition, therefore, it is an energy minimum with respect to every coordinate except the coordinates that we are investigating. And you will be doing that in your homework. You will be taking a methane molecule and slowly pulling a hydrogen off it, and then re-optimizing at every distance the rest of the coordinates into a minimum. And so you would go there, 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 and you can see that's a step, reoptimization, another step, reoptimization, another step, reoptimization, and so on. Eventually you would reach this transition state. And it is quite important there. In fact, you might go astray, right? On a different energy surface, that process will keep climbing, 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 perhaps into some other transition state with respect to some other irrelevant coordinate, but you will drive your system into a maximum that is different to the local maximum that you want, that represents your energy minimum energy pass to the products that you want. You might arrive at a different product. And so here, quite a lot of chemical intuition is required. That's an example of benzene, cyclohexane ring isomerization from the boat to a chair conformation. And you can see that a well-chosen reaction path does pass through a neat maximum that connects these two energy minima, but it's quite easy because there are so many coordinates to end up somewhere else that is not in fact the correct maximum in here, and so you have to watch it. One bulletproof way of doing this, but a very expensive one, is called hypersphere search. You could in principle just take your starting coordinates in the multidimensional space of every Cartesian coordinate of every atom you have, and just scan every displacement there is by a particular radius in that high dimensional space. This is very, very expensive, particularly in spaces of, a few dozen and more dimensions, but of course this will map every reaction path out of the structure that you have. But this is not very often used because, well, for anything bigger than really a 3-atom molecule, this is practically computationally unrealistic. What we could also do is say that, okay, in chemistry, right, every reaction really begins its life as a vibration. You put enough energy into a particular vibration, it vibrates a little bit too far, and the reaction happens, at least, some dissociation process. So we could start at this beginning, the initial point, calculate the Hessian, and take a look at the normal modes. Pick up the normal modes that we like, the vibrations that we would like to result in some bond breaking, and just step uphill. So we start at the minimum, we compute and diagonalize the second derivative matrix. We move in the direction of the eigenvector that we are interested in, so we look at the vibrations, we pull that vibration further and step in the geometry in that direction. Could be user-specified step, could be something dynamically decided. We recalculate the gradient and the Hessian, we rediagonalize the Hessian, and we also take care to minimize every other coordinate into a minimum. So we take downhill steps with respect to every other coordinate except for the coordinate of interest. And that keeps the rest of the molecule happy, and there's only one evolving process that might lead to something falling off. And so we repeat these steps until we have gotten somewhere interesting, and that's an example of what's going to happen. So pick a direction, step reoptimize, step reoptimize, step reoptimize. Eventually you will get into that transition state, assuming you are careful enough with steering here. So this is very robust. It does guarantee that you will converge into some saddle point. Whether it is the saddle point that you're interested in is again up to sheer luck and experience in a lot of cases. For small systems it mostly works. For big systems, well, problematic. Very expensive again, because the Hessian is recalculated at every step, and if you've got more than 50 coordinates, then visualizing these high-dimensional spaces to find out where your molecule goes can be a little bit difficult. That's an example from this paper of a transition state being found. So that, I think, is a minimum. That is one saddle point, and that's another saddle point of a particular energy surface, and you can see that the algorithms are generally, with a bit more trouble or a bit less trouble, end up in the correct places that correspond to the transition states in them. One obscure mathematical method to move from one transition state to another is called gradient extremal following. We can define a curve on some potential energy surface as such a collection of points where the gradient is an eigenvector of the Hessian. Very hard to imagine chemically what this might mean, and in fact it doesn't have any chemical meaning, but mathematically these curves, they connect stationary points. So if you trace enough of them out of one stationary point, you will discover all the nearby stationary points. And that's a different way of recasting the same thing, in this case variationally. So every point on a gradient extremal path is the minimum of the gradient modulus subject to a constraint on the energy. So they are parameterized by energy. They may be used for stationary point search. That is one of the possible iterations that you can do for them. I will not go through the technicalities in here. And I will only note that both the gradient extremal path and minimum energy path, they can be quite complicated and can bifurcate in stationary points of higher order. And so if you are searching through a particularly complicated reaction path, you would probably want to visualize your molecule at every step and deploy a little bit of chemical intuition to find out where the atoms are actually moving, because visualizing things in high-dimensional spaces can be quite a bit of a pain. Okay, so that was, let's say, the less obvious and the more user-driven methods that get you transition states of quantum mechanical systems. Of course, later work has emphasized automation. It should be possible, if you know the initial geometry and the final geometry, to somehow automate the transition state search. And one of the simplest ways of doing it is called linear synchronous transit. We decide a suitable reaction coordinate system, so usually internal coordinates for typical molecules. We say, well, okay, that's our reactant, that's our product, why don't we just draw a straight line in the coordinate space and evaluate the energies, and then hopefully the maximum that we find on that path would be a reasonable initial guess for our transition states. So that's our reactant coordinates, that's our product coordinates, that's linear interpolation. And so we've got these coordinates as a function of just one path length parameter, calculate the energies on every point of that path, find the maximum, use that maximum as the initial guess for transition state optimization. Sometimes works, sometimes doesn't. You may just get this maximum too far from your true transition point. People have improved it somewhat. You might actually guess your intermediate. So that's your reactant coordinate, that's your product coordinates, that's your guess coordinates at where the intermediate might be. And that is a quadratic interpolation, so quadratic synchronous transit in this case. Again, produce the complete path, compute the energies on that path, use the maximum energies that you found along that path as the initial guess, for example, for a quasi-Newton optimization of the transition state. So get the energies for reactants and products, determine the maximum energy structure, and then refine the maximum energy structure as soon as it's converged. You've got, well, a good stab at your transition state. So this is called synchronous transit guided quasi-Newton. So we use the synchronous transit curve to get a guess, and we then refine that guess by a quasi-Newton optimization. Even that is quite prone to errors, because even a quadratic curve might not be a very good approximation in complicated rearrangements in large molecules. And a somewhat better version of the same is called plane elastic band method. We take our initial state, we take our products, and we just create a number of beads on an elastic band, quite literally. So these are coordinate points on that surface, and we add the additional term to the energy that tensions this band. So that is the coordinate of every bead, and then we say, well, okay, the energy is the sum of the energies at all of the green points, but also some tension, so the distance between the adjacent green points, some force constant squared. So we want that band to be tensioned, and we want these beads to have some mass. And so then we just release those beads, and what will happen is it will hopefully fall and roll down the surface and produce something that does resemble a reaction path. Of course, the trouble with this is that these force constants are unphysical, and so what is going to happen is, if you have such a potential energy surface and the true minimum path is here in blue, then the tension will cause some of the points to rise, and so the maximum in here would once again only be an approximation to the true transition states, which you would then refine. And if your force constant is large, then you will literally lift these points. If it is small, then most of them will fall into a kind of local minimum, but then you need enough of them to actually approximate your true transition state in there. So we need to eliminate this somehow, and the process that eliminates that is called a nudged elastic band approximation. So here we had problems because there were components of this force perpendicular to the path. Why don't we just project them out? So what we can do then is say, okay, the nudged elastic band force is the force that is generated by the gradient of the potential, but only in the direction that's perpendicular to the path. And the force of the string of beads, right, so the Hooke's law for beads, must only act parallel to the path, and so we are nudging the string perpendicular and we are tensioning it in parallel. What this means is the string wouldn't move, only the position of the beads on the string will move under this force, and the string will be nudged by only the genuine physically relevant forces on the system. And that's an example of it. So you've got one minimum, you've got another minimum here, and you've got this nudged elastic band that passes through a couple of transition states on the way. Of course, you do need enough beads, but it does work. So the advantages, it does get you the minimum energy path, wouldn't need any Hessian information. Notice that this is formulated in terms of gradients, so you can use BFGS. Does produce a continuous minimum energy path, and in fact these individual points there can be sent to different nodes of a cluster, and so easy to parallelize. But then you need enough beads, firstly. Then there may be multiple minimum energy paths, so for example through here. Right? No guarantee that you found the right one. And then the saddle point, of course, might fall between these beads and still might need further refinements. And if this thing is particularly hilly, then you would have slow convergence, because this time you need to converge not just one point, you have to converge the entire path. Thankfully, all of this is implemented and reasonably automated in Gaussian. So in your homework for very simple, the tiniest of systems like methane and hydrogen atom, you will try all of these things and, well, get some experience with them. Practically speaking, there's another caveat in that transition states involve bond breaking, involve isomerization, involve charged intermediates, involve all sorts of things that might not be the ground state, or might make the ground state multi-reference, because different ground states will be competing for what the molecule is to become on either side of the reaction, meaning that single reference methods usually fail. If you look at these. So that's Hartree-Fock, single determinant method. Bis-Relip, that's DFT, previous generation, and MO5 is the current, one of the current best ones for the task of calculating the minima. If we look at the transition state energy, so the gray here, the gray block is the experimental, and these are just different molecules, doesn't matter what they are, but you can see Hartree-Fock is of course wildly off in a lot of cases. Sometimes not even the sign is correct. This is truly ridiculous, right? But even the latest exchange correlation functional in DFT can be off by more than a factor of 2. And so when you are fishing for transition states, you need multi-reference methods, like multi-reference configuration interaction, or multi-reference coupled cluster, or multi-reference Hartree-Fock, but so long as you have some character in your reference wave functions that does permit it to be, for example, degenerate. So be careful there. In a lot of cases, the subtle parameters like transition state entropies are wrong at every level. So that's delta S of the activation complex there. So the experimental value is 14. I think it's kilocalories, or maybe actually calories per Kelvin mole in here. And you can see all of the calculations are wildly off, not even the correct order of magnitude in there. So tough luck. And that's another notorious example. So rotational barrier in benzaldehyde, because there's conjugation involved between the double bond of the aldehyde group and the aromatic system. It's a significantly multi-reference problem, and you can see the experiment is 5, whatever it is, probably kilocalories per mole, and pretty much every method except super sophisticated multi-reference configuration interaction methods is basically just dead wrong. So with transition states, be careful. And of course, STO3G Hartree-Fock is just a cancellation of errors, right? It got close by pure coincidence. It should have been a lot further back. So that is the health warning, so to speak, associated with transition state calculations, in that the model Hamiltonian that you need for them does need to be quite sophisticated. Another picture of gradient extremals. You can see they're quite complicated. That's a minimum, that's a saddle, that's probably a minimum, that's another saddle, that's another minimum. You can see you can get pretty lost if you follow some of these curves. Another important thing is that transition states are often charged. You would have, as a result of bond breaking, possibly charge separation. And then remember that the dielectric constant, for example, in water, is 80, which means that Coulomb interactions through water are a factor of 80 weaker than they would have been in vacuum. And this factor of 80 is, of course, a colossal difference. And so what you're going to have is, if you run your transition state calculations in solvents of different polarity, and how to deal with solvents we will look at in one of the next lectures, you can have very different energetics, right? You can get a factor of 2 error in the transition state energy. You can miss some intermediate minimum completely and get the second transition state energy and even the product energy completely wrong, because electrostatics is not correctly taken into account. So that's the other thing to worry about in those cases. And well, unfortunately, the convergence of saddle point optimizations can be slow, can be erratic. The simple calculations that you've been doing so far for small molecules, they converge in 10 or 20 BFGS iterations. That is no longer the case for transition states. You need to have some patience, and in a lot of cases a significant amount of luck to actually get all of that corrected. Right, so there's a number of miscellaneous notes in here, more or less summarizing the fact that at this level, molecular geometry optimization is a dark art. You need to have sufficient experience trying and failing before you become good at it. Firstly, there is always the convergence criterion, right? Remember the self-consistent field for the Hartree fork or for DFT or whatever post-Hartree fork methods you have there, had convergence conditions, right? If the energy changes by less than a certain amount, if the gradient is smaller than a certain number, if the density changes by less than a certain number, then we declare, okay, this geometry is good enough. But then gradient calculations are an extra calculation on top of that geometry, and so typically a couple of orders of magnitude tightening is necessary in the convergence criteria to enable the calculation of accurate gradient. Thankfully, most electronic structure theory packages these days do it automatically. The moment they see that the user is optimizing the geometry, they automatically tighten the convergence conditions on the energy. If you have some flat ring or some linear system like fused acetylens, do not use Z matrices or internal coordinates because you will have invalid dihedrals in them. Use Cartesian coordinates, they just move it atom by atom. The convergence is going to be slow, but at least it is going to converge. If you have an extended system like a lengthy keratin, be careful, small displacement of some angle might move some atom much further away by a couple of angstroms. In that case, your calculation would never converge because, of course, the displacement of that atom would never be below the convergence conditions that you've set upon it. So either avoid using internals in that case or set appropriate convergence conditions on your geometry. Van der Waals complexes, non-covalent interactions, of course, rely on polarizability. That is a parameter that Hartree fork and DFT get consistently wrong. So for Van der Waals complexes, you need serious post-Hartree fork. There are DFT methods that claim to reproduce it, but really they just have classical 1/r⁶ artificial addition there. So avoid them if possible. Non-covalent interactions, you need high-level configuration interaction, coupled cluster or NP2 to properly reproduce. And of course, because they're non-covalent, right, the energy minimum can be quite shallow in that case because the energy of those interactions is so small. So that can be difficult. If you do know a very good approximation to a minimum, for example, from a crystallographic database, those geometries tend to be really good. If you've pulled a geometry from the X-ray structure database, distort it a little bit before you start a quantum chemistry optimization, because if you are starting very close to a minimum, the minimizer would not know where to step. It will try stepping too far, fail, try stepping less far, fail, try stepping less far again, fail, and then crash out. So actually starting from the initial conditions that is too good, ironically, can cause the calculation to crash because you would confuse the minimization algorithm. Positive definiteness, of course, if you're looking for the minimum and the calculation is something very consequential and important, always run the Hessian and check that it is positive definite. If you start too far from the minimum and too close to some stationary point, as you saw in one of the previous slides, the algorithms will cheekily converge into that stationary point that might not actually be the energy minimum you're looking for. And finally, we will talk about implicit solvent models in the next lectures, but typically what that involves is a cavity that is drawn around the molecule and digitized, so the cavity will have vertices and faces, and of course it's a discrete object, right? You are discretizing what is a continuous bubble around the molecule, and that discretization creates additional numerical noise, and that complicates the geometry convergence. So optimizations that involve solvent effects, they would rarely converge to the same accuracy as the optimizations in vacuum, because solvent cavity rearrangement creates an additional source of energy variations, additional source of numerical errors, and additional confusion for the minimizer to handle, because the gradient might change abruptly because, for example, some point got inside and got dropped from the solvent cavity. Okay, so well, all of that will become clear eventually once you've had some practical experience generating all of this and optimizing all of those molecules. The final point to make is, in a lot of cases, you are dealing not with a molecule in vacuum, you are dealing with a material. Some nitrogen vacancies center in diamond, some phosphorus vacancies center in silicon. Whatever it is that your quantum device involves, might be something as basic as molecular dynamics simulation of a protein in water. In all cases, this is no longer vacuum. This is either condensed phase liquid or a condensed phase solid, which is infinite in every direction, and then we need to approximate it somehow, and that's the way of doing that. The periodic boundary condition, essentially, if the atom moves out of this edge of the box, it reappears from the other side, much like it happened in ancient computer games, you know, on 8-bit gaming consoles. So the world is boundless in every direction, but nonetheless does have a finite volume. That's called the periodic boundary condition. This container, so the elementary cell of this, of course, has to be large enough to avoid self-interaction. So the atom should not be so close to its own image in the nearby cell as to effectively interact with itself. So the thing needs to be chosen, usually empirically, by whatever accuracy criterion you can think of. This elementary cell needs to be big enough, at least 10 angstroms in condensed phases, so 10 bonds. A CH bond is approximately an angstrom, is recommended in practice. And then, of course, it doesn't need to be rectangular. You can have hexagonal periodic boundary conditions if the unit cell of your crystal is hexagonal. So long as it's a complete tiling of 2D or 3D space, then that's okay. The periodic boundary can be two-dimensional rather than three. So if you have a surface, for example, a surface is periodic in 2 dimensions, but not periodic in the third one, in which case you would have some combined conditions, whatever it is, vacuum that you have on the non-periodic coordinate and the periodicity on the other two. Again, in Gaussian, these things are automated. If you click periodic boundary conditions in Gauss view, you will be able to set them up. What is important, of course, it's not just atom positions that we will be optimizing in this case. Even the dimensions of this unit cell become adjustable parameters, right? If the atoms are not densely enough packed inside the unit cell, it makes sense to shrink the cell volume, which would, in that case, reduce the energy and be a legitimate optimization step. So you will discover that the programs that deal with periodic boundary conditions will also optimize your cell parameters in periodic calculations, not just the geometry of whatever sits within. One important point as well is to balance the charges if you have an unbalanced charge within your unit cell. For periodic boundary conditions, that means infinite total charge. Coulomb interactions are 1 over r. The integral becomes singular, goes to infinity. So even if you have a tiny unbalanced charge in the unit cell, that would blow up your total energy for the PBC calculation. So always make sure that the total charge of the unit cell adds up to 0, to exactly 0, before running the periodic boundary conditions. And I've already mentioned that you can have 2D and 3D boundary conditions, or even 1D if you have some particularly lengthy linear molecule. Okay, that's me for today. So as you can see, finding transition states is much more of a dark art than simply optimizing the geometry into a minimum. Some of you will have quite a lot of exploration of this exact topic. I'm looking at Luke, who will be calculating the thermodynamics of conformational transitions. So in your case, the transition state is some amino acid isomerizing itself inside the protein when the protein changes its conformation. So this is very practical for some of you. Others will only use these calculations as sources of magnetic parameters in your quantum devices, right? So computing spin Hamiltonian parameters and so on. But in all cases, the first stage of those calculations is getting the minimum energy geometry and making sure that that is in fact the geometry that you need, and these are the various things that you will encounter in the process. Any questions?